Good morning and welcome you all to this session of the course. In the last class, we were discussing the work required or work done to the fluid and the pressure rise. Let us again continue little bit the earlier discussion. We were trying to express the compression process thermodynamically in Ts plane by showing two pressure lines, constant pressure lines. One is the total pressure at the inlet to the compressor, another is the total pressure 3 at the outlet to the compressor. No, it is 3 at the outlet to the compressor, which includes the diffuser too. That means, if you see this figure, you see that this is the inlet to the compressor, that is the impeller, and this is the outlet, the final pressure rise. If we just show this P3T and P1T, I want to find out the total pressure rise in the compressor. So, now in this case, if the entire process is isentropic, then we can show the process in the Ts diagram, as I already told that this is 1 and this is the T1T, this is the T1T and this is the T3T, this is the T3 dash T. Rather, this is T3 dash, T3T dash, T3T dash. This is the actually process. We just state 3. Let this be 3 dash. This is an ideal process, and the actual process, as I told, which incurs the internal irreversibility due to fluid friction and internal heat transfer due to temperature gradient, and we land up to the actual point 3, which heals right this way to increase the efficiency. This was well known. Now, the work per unit mass, as we found, or energy per unit mass from the steady flow energy equation is Cp. This is T3T, this is T3T is Cp T3T minus T1T. And at the same time, we found from the momentum theorem, which is known as Euler's equation, that E by m equals to psi, the power input factor, into sigma, the slip factor, into the U2, the peripheral speed at the outlet square, at the outlet of the impeller square. Okay? So, this is the energy. Now you see, if we want to relate the pressure rise in this process, then the pressure rise can be written. So, pressure rise can be related through the isentropic process by the isentropic process relation is like this P3T, that means this pressure and this pressure same, that same pressure line divided by P1T is T3T dash, that means it is through the isentropic process, that is the end of the isentropic process, T1T to the power gamma by gamma minus 1. Now, if we have to relate this T3 dash to T3T, we have to take care of the isentropic efficiency of the compressor. As I told you earlier, the isentropic efficiency is defined as the ideal work done in absence of any friction or internal irreversibility in the process to the actual work done to the fluid or actual work input with in consideration of the friction. In this case, the actual work input is more than that in the ideal case. So, therefore, if we write that, the ideal work done from the steady flow energy equation will be this. This is found from the isentropic case, and similarly, by application of the steady flow energy equation, it is like this. This is the actual work input, and since air is an ideal gas with constant Cp, Cp cancels out, this becomes this eta C. Okay. Then we can write the T3 from this, we can write T3T dash divided by T1T is equal to what? Eta C into this, eta C into T3T minus T1T. This is divided by T1T plus 1. Am I correct? Because this divided by T1T is this by T1T, eta C into T3T minus T1T divided by T1T, okay, plus 1. So, this is the, so now if it is okay, now if we this I will use, if we now, okay, please wait, this, if now we use this expression here, then we can write that P3T by P1T equals to what? T3 dash by T3 is this, that means 1 plus eta C into T3T minus T1T divided by T1T to the power gamma by gamma minus 1. Again, I can substitute this temperature difference T3T minus T1T, the difference in the stagnation temperature at the end of the compression, that means the end of the compressor, after the compression in the diffuser 2 and the inlet stagnation or total temperatures, this difference in terms of the work per unit mass, we can write 1 plus eta C into this will come sigma psi sigma power input factor U2 square. So, this is E by M. Now, we are replacing this thing divided by Cp T1 T. Sigma not visible. Oh yes, I am sorry that it is not visible. Now it is visible. So, this we can now write to the power gamma by gamma minus 1. So, here you see that the pressure ratio, which is an important parameter for the compressor, is expressed in terms of the peripheral speed of the impeller at its tip. Now, here what happens is that sigma is usually not a variable one, it lies between, as I told earlier, some value around 0.9. Eta C is the compressor isentropic efficiency, this value is almost fixed to something like 0.85. Now, for a given inlet total temperature, therefore, we see this pressure ratio is proportional to the impeller speed in this fashion. So, this is a very important relation for the pressure ratio to impeller speed. Now, I will come to a very important thing of the centrifugal compressor, not centrifugal or axial compressor. Now, as I told earlier, since the compressor handles fluid which are compressible in nature, they are gas, they are not liquid, their bulk modulus of elasticity is little less. So, therefore, depending upon the flow velocity, the density changes, and if the change of density is appreciable, flow is compressible. And in compressible flow, first consideration is that the change in density with pressure. There are other considerations depending upon the flow regime which takes place in compressible flow, which I will discuss afterwards when I will be telling you about the compressible flow, that depending upon the flow regime, especially when the flow velocity is very high, some typical features which are typical to compressible flow take place. If the flow velocity is very high and close to the acoustic velocity or the velocity of sound relative to the fluid at that state, then a different physical pictures are observed. So, therefore, in a compressible flow, one of the very important criteria to specify the flow is the ratio of the flow velocity to that of the sound velocity relative to that flow at the state of the fluid, and that dimensionless number is known as Mach number. So, therefore, I write you a Mach number consideration, and this is for all machines or all device that handles compressible flow or the flow of compressible fluids, Mach number, that is MA, which is defined as the ratio of the flow velocity divided by the velocity of sound or acoustic velocity. This is the velocity of sound, acoustic velocity. A is the velocity of sound or acoustic velocity, velocity of sound or acoustic velocity relative to the fluid flow at that state of the fluid. So, it very much depends upon the state of the fluid. State means, for example, density and temperature of the fluid. So, this is a very important criteria, and when the flow velocity equals to the sound velocity, then Mach number equals to 1, and we call the flow as sonic flow. This flow is called as sonic flow. When the flow velocity is less than A, Mach number is less than 1, the flow is known as subsonic flow, subsonic flow. This will be discussed afterwards. Just a introduction I am giving you so that you can understand things. When this is greater than A, that is Mach number greater than 1, the known as the broad classification, supersonic flow. And there is a regime in the subsonic flow when V is less than roughly 0.3 A or Mach number is less than 0.3, then the flow may be treated as incompressible flow. Incompressible flow. You understand? Incompressible flow. That means the density does not change with the pressure, or the change in density with the pressure is negligible. Okay? Relative change in density is negligible. So, these are the regimes of flow. Now, what happens if the flow is supersonic at any stage depending upon its velocity, then some features are observed which causes extra losses of energy, and in compressor which causes extra losses of static pressure, okay, which is undesirable. So, therefore, for compressor design one has to be very careful that Mach number of flow should not exceed necessarily or usually at any point of flow in the compressor over the sonic level, so that other complicated features of compressible flow will come into. So, this is known as Mach number considerations. So, therefore, at each and every section of the compressor, the Mach number has to be considered, and here the Mach number, if you see the definition, that in the definition the velocity of flow, it is the velocity relative to the moving solid surface. So, when there is a flow velocity past the solid surface, it is the velocity relative to the solid surface, and in a turbo machines the solid surface are also moving, solid surface has also the velocity. So, therefore, the relative velocity of the fluid has to be considered in defining the Mach number, which has to follow this criteria of being less than 1 to make the flow subsonic to avoid excess losses. So, one of the important section is the inlet to the impeller. Actually, the Mach number velocity of flow will be high at the outlet of the impeller, where it gains kinetic energy from the impeller, where the energy is being imparted to the fluid. So, to restrict that Mach number, which is maximum at the outlet tip, we have to check the Mach number at the inlet of the impeller too. So, therefore, the inlet design has to be made in such a way that Mach number is relatively low. Now, you see an inlet section of the impeller, that is the inlet part, this is known as inducing section of a centrifugal compressor. You see, this is the eye, this is the root of the eye, and this is the tip of the eye. So, this is the tip diameter of the eye, and this is the root diameter of the eye, and this is the passage of the flow, normal flow. That means, it is the cross sectional area of the flow velocity. The flow turns like this, try to understand very well, like this. So, therefore, the design of the tip should be such that the Mach number should be low. Now, how do you define Mach number? Just I told you at this moment that Mach number at entry to the fluid here, if you define, it has to be defined based on the relative velocity, that means VR1 divided by A. Now, A depends upon the fluid state here, but the VR1 depends upon how the fluid is being allowed to enter to the impeller eye. Now, as you remember, the impeller is like this, the impeller design. Again I show you, the impeller blade is like this, at the eye the design is like this. So, this is a velocity triangle, you see, that this is the relative velocity whose angle matches at the angle of impeller blade at the inlet. Now, these two are specific or typical velocity diagram. This diagram is for a very large impeller diameter, where the peripheral speed is more u1, okay? And because of the large diameter, the frontal area becomes large, for which the flow velocity or the absolute velocity is less, which gives rise to a higher relative velocities, and we have to be very careful. Here the Mach number will be more, but at the same time the mass flow, it can accommodate more mass flow. Okay. But if you now reduce the velocity, this is the typical diagram of a small I tip diameter. There what we will get? We get a u1 like this, is relatively lower than this, but the flow velocity is high, so that VR1 may be reduced. But it is very difficult to conclude which one is greater or lower. That depends upon the relative values of u1 and the value of V1. However, this VR1 is of our prime importance, such that VR1 by A, that is the ratio Mach number, should be low, and we try to design the impeller tip in such a way that the Mach number lies between 0.7 to 0.9, usually 0.8, so that we avoid losses. What happens, I tell you in little brief, which will be discussed in more detail when I will teach you the compressible flow. What happens if the flow is supersonic? That means in a compressible flow, if the flow velocity is more than the acoustic velocity, local acoustic velocity, then what happens, if under certain boundary conditions or in the disturbance of the flow, flow has to adjust and accordingly decelerate, then the supersonic flow suffers a sudden deceleration through a sudden discontinuity, and that discontinuity is known as shock. So, therefore, a shock takes place. A supersonic flow cannot adjust itself to have a gradual and smooth transition in the form of deceleration from supersonic to subsonic. It cannot happen. And in compressible flow, when the flow is supersonic, due to the circumstances or the boundary conditions imposed on the flow, flow has to decelerate, and this is adjusted by a sudden deceleration or a sudden discontinuity in the flow, and this discontinuity is a really mathematical discontinuity which takes place within almost infinite small region whose length is in the terms of molecular diameter, and that sharp discontinuity in the flow is known as shock in general. And that shock, what matters to the practical case is that due to that shock, there is a abrupt loss in the total energy. This is a totally irreversible process. So, what matters is that, because you can ask me, sir, when the deceleration takes place, when the fluid comes to subsonic stage, what happens, that pressure increases? Yes, static pressure may increase, but if you consider the total mechanical energy, there is a huge loss in the total mechanical energy. Some of the pressure part, that is pressure energy you can call loosely, and the kinetic energy, there is a loss. So, therefore, in design of any compressible flow machines or compressible flow device, one has to be very careful. First of all, it is better to avoid the supersonic state of flow, and or supersonic state of flow is unavoidable. One has to be very careful, so that supersonic flow should be decelerated in a way that shock does not take place. Here again I am telling you, which I will explain afterward, it is not that always shock will take place. It depends upon certain boundary condition imposed on it, so that shock has to take place. But it may occur that flow may be made in such conditions with design back pressures and many other things that I will discuss afterwards, where shock may be avoided. But in practice it may not be done, because the supersonic flow, when it comes, for example, when an aircraft moves with a supersonic velocity, as you know that when aircraft moves with a supersonic velocity, that is velocity more than the sound velocity at the state of the fluid there at high altitude, then what happens, relative to the aircraft, the fluid moves with supersonic velocity. So far upstream, the fluid approaches the supersonic velocity. When it approaches the nose of the aircraft, then what happens, the fluid has to decelerate. Fluid has to decelerate when it tries to strike the nose and flow past the nose, and that deceleration is causing the shock, and an oblique shock occurs at the nose of the aircraft. So, these are the things probably you know today, these are popular things. So, therefore, I must say that this Mach number consideration is very important consideration, and therefore, the impeller eye design has to be made so that Mach number at inlet, that is based on the relative velocity at inlet, should be low. Thank you.